Let's revise the entire topic of waves in GCSE Physics. Okay, well, starting up with the two types of waves. We can either have a transverse wave in which the vibrations are perpendicular to the direction of travel of the wave. So, for instance, we can have this wave which the wave itself is moving here, but the particles are moving either up or down, which is at 90 degrees to the direction of travel of the wave. We can also have longitudinal waves in which the vibrations are parallel to the direction of travel of the wave. So think of it kind of like compressions in something like an accordion. Also sound waves, a typical example of longitudinal waves. So let's add this as an example. So sound waves, whereas our transverse wave, a perfect example for that would be something like a water wave. It's really important to note that in all the waves, the particles are not moving in the direction of travel of the wave, just the energy of the wave is. So in a way, it's the wave that's moving, not the individual particles. The particles are either just going up or down, almost a little bit like a Mexican wave at a stadium during a football game. And now let's go for a couple of important definitions. We're going to start off with the amplitude. This is the maximum displacement of the wave from a point on the wave to the equilibrium. So in this case, the equilibrium is just this horizontal line, and you can see that displacement is the greatest here, and you could also have a negative amplitude, which will be exactly the same as long as the amplitude doesn't vary. In my sketch, they're not exactly equal, but I have drawn this by hand. Okay, anyways, the wavelength is the distance between a point on the wave to an equivalent point on the wave. What do I mean by that? So something like the peak to peak distance is a very easy way of finding the wavelength. So the peak to peak distance right across here will directly give us the wavelength. For the wavelength, especially if you do A-level physics later on, you will come across this symbol that is commonly used, is the Greek letter lambda. Okay, frequency is the number of wave cycles passing per second, and that is measured with the units in the unit of the hertz. You can also have the time period, and that simply is the time that it takes for one complete oscillation or one wave cycle. Those two are related by the famous equation that the time period is 1 over the frequency, and mathematically we could write that as t is equal to 1 over f. Equivalently, if we just swap those around, it's also true that the frequency is equal to 1 over the time period. And those are two really important equations. Now this here is known as the wave equation, and is one of the most important equations that comes up every year on the GCSE Physics exams. So wave speed is equal to wavelength multiplied by the frequency. Mathematically we can write this as v is equal to f times lambda, where v is the wave speed, the wavelength is given by lambda, and frequency is given by f. Okay, well, shall we just rearrange this for all the other possibilities? Because of that, we can also write this as the frequency is equal to the speed divided by the wavelength. Or we can also say that our wavelength is equal to the speed divided by the frequency. In terms of the actual units of this, so the wave speed is just measured in meters per second. The wavelength is measured in meters, and the frequency is measured in hertz. You can also do a fun little experiment to measure the speed of sound. The main idea and equation that we're going to be using is that speed is equal to distance over time. So we're going to be producing a sound quite far away. So typically we just have one person, and all they're doing is they're just clapping two wooden blocks together. Now if we're over here on the other side and we have a timer or a stop clock, what we're going to do is we're going to start the timer when we see the person actually when we actually see the impact. And we're going to stop the timer only once the sound has actually traveled, and then we can stop it. And this will be the time that it actually took for the sound to travel. We're going to take multiple measurements and then we're going to average. Measuring the time in this case, this is where the tricky bit is. This distance will be quite far. In practice, when you do this experiment, somewhere between 100 and 150 meters works really well. So let's just say 100 meters. We're going to measure this distance either using a very long tape measure, or one of those measurement wheels tend to work really well. And once again, taking multiple readings and averaging them out works really well as well. You can also do a very similar experiment to measure the speed of water ripples. The first thing that we need is to actually have a method of producing the water waves. One very easy way would be to have some sort of a weight, and all we need to do really is just vibrate this up and down a tank, a ripple tank, and this will produce a wave that will be traveling in this direction. We're going to be measuring the distance that it travels. In this case, this will be this distance here. Let's call that D. And we also need to measure the amount of time that it takes. As always, we're going to take multiple readings and average, and finally we're going to use speed is equal to distance over time, and this will give us the speed of the water wave. It's important to know that waves can be reflected at the boundary between two different materials. Now, what do I mean by this? Imagine that we have something like a mirror, and let's have a ray of light which is coming in. So we have a ray of light which, say, strikes this surface across here. It can reflect, and if that's the case, the rule is that the angle of incidence will equal to the angle of reflection. So it was 48 before, and it's going to be 48 afterwards. And we can see that this here is an example of a reflected ray. So a wave can also be fully absorbed at a boundary, and in this case you can see the wave is going in, however none of it has been reflected, it has been fully absorbed. It can also be transmitted. The wave can also be transmitted at the boundary between two materials, so this is also known as refraction. And here's one example when we have a light ray or some sort of a wave that is coming from air to glass, and some of the wave will be transmitted. Okay, now let's talk a little bit about sound waves. Now, the way sound actually works is because sound waves can travel through solids, and that causes the actual solid itself to vibrate and a wave to propagate through the solid. One example is the ear, and within the ear, the eardrum starts vibrating at that frequency, and the sound wave gets transmitted to your brain, causing the sensation of sound. Now, the conversion of those vibrations of the air particles, which is sound, to the vibrations in your eardrums can only happen over a limited frequency, and this is what actually restricts the limits of human sound. So most humans can only hear somewhere between 0 and 20,000 hertz. You might come across this written down as 20 kilohertz. If you are asked in an exam question to discuss sound waves, this answer here will always give you full marks if the question is asking you about this. And now let's have a look at some waves for detection and exploration. So in general, in waves, we can use the differences in velocity, the absorption, the reflection between different types of waves and solids, both to detect and to explore structures which are hidden from direct observation. So for instance, if we're shooting off a wave and we get nothing back, this means that the wave is just carried on. However, there's a surface here we might shoot a wave, but then it might reflect and then it will come back. Now this could tell us that there is a structure here because the wave has well returned. An example of this, for instance, is ultrasound, which is extensively used in medical physics, for instance, but some of the waves are reflected when they meet at a boundary between two different media, and the time for the reflection to reach a detector, for instance, we could place a detector across here, can be used to determine how far away the boundary is, using speed as distance over time, because we know what the speed of sound is. This allows the ultrasound waves to be used for, as we said, both medical and also for industrial imaging. You can also have seismic waves, which are produced by earthquakes, and it's important to remember for the exam that the P waves are longitudinal and they travel at different speeds. The S waves, on the other hand, are transverse and they cannot travel through a liquid. P waves and S waves provide evidence for the structure and the size of the Earth's core, and this is really important and interesting. You can also have echo sounding, which uses high frequency sound waves in deep water to essentially measure depth and explore the surroundings. Now let's talk about electromagnetic waves. First of all, they are transverse waves. This means that the electric fields in this case will oscillate perpendicular to the direction of travel of the waves. They transfer energy from the source to the observer, and they also all travel the speed of light regardless of their frequency. Okay, now they come in a spectrum, and if we have a longer wavelength, so let's just say that we have an increasing frequency this way. So let's start with the frequency, increasing frequency, and also you can think of it as decreasing wavelength. So let's just say it like this: decreasing wavelength. Okay, so what does that mean? That means that radio waves will have the longest wavelength, but the shortest frequency. And then we have microwaves, infrared, visible light is somewhere in the middle. Then we have ultraviolet, X-rays, and then finally we have gamma rays, which have the highest frequency but the shortest wavelength. There are lots of different examples of transfers of energy via electromagnetic radiation. For instance, you can have the sun, as illustrated by my drawing across here. That transfers energy to the Earth, even though there's the vacuum of space. However, the electromagnetic waves travel from the sun to the Earth, and that's how we get our energy and we are alive. There are also other different examples. I mean, you can have something like a laser, which will transfer energy from one location to the other. Something like an infrared lamp, for instance, will transfer energy. Loads of different examples, but you need to recall a few for the exam. And now let's talk a little bit about refraction, or the transmission of waves, and these ray front diagrams. Okay, so you may come across these diagrams, and this distance over here between the lines, this is actually equal to the wavelength. Okay, well, now during transmission, the frequency of the wave remains the same. The way we write this as F is equal to constant, and this is during refraction. You may also hear this being called transmission, but refraction, transmission, kind of the same thing. Okay, so the frequency is equal to a constant, and what actually happens to the wave if we're going to a substance with a higher what is known refractive index. For instance, let's say that this here is water, then the speed will go down, so the ray will slow down. If that's the case, the wavelength will also decrease. Now this means that as the ray is going in, its wavelength will become smaller, and we can see that this distance here from one wavefront to the other has decreased within the water, and the whole ray has bent towards the normal. Here are a couple of notes. So radio waves are actually produced by vibrations of electrical currents in electrical circuits, and this is actually how mobile phones work and radio as well. So when radio waves are absorbed, they actually create an alternating current with the same frequency as the radio itself, and the radio waves, when they're picked up, create those oscillations in electrical circuits, and this is essentially how radio works. I mean, it's just essentially a piece of wire, and there's some electrons across here, and when the wave strikes them, they start moving with the same frequency as the incoming wave, and this is how radio works. It's pretty incredible. Okay, well, now how is EM radiation actually produced? And it actually changes within the atoms themselves by the movement of electrons, which originate electromagnetic waves. Anytime an electron drops down in something called an energy level, then that emits a particle of light, and this is how all EM radiation is created in a way. And gamma rays as well originate from changes within the atom. Okay, we also have some of the EM radiation can have pretty bad consequences in the human body. So we've got ultraviolet, X-rays, and gamma rays. These can be hazardous, and radiation dose is typically measured in sieverts, or ionizing radiation, something to be aware of. Now, what are some practical applications? Loads of different ones. So these are the easy questions on exams. So radio waves, for instance, they're used in television and radio. Why is that? Well, they travel at the speed of light, and they can also be they're also used within electrical circuits, so it's very easy to send a signal. Microwaves, they're used in satellite communications and with cooking food. Actually, they are vibrating at the same frequency as hydrogen, which allows us to resonate the molecules in the food. We also have infrared, which is being used in heaters and in cooking food, and infrared cameras. We've got visible light, which is used in fiber optic communications. In fact, you're also looking at this video through, well, visible light. Also ultraviolet, which is used in sun tanning, for instance, and X-rays and gamma rays in medical imaging and treatments. Now let's have a look at lenses. In order to illustrate that, I'm using a website known as Hyperphysics, which has some brilliant diagrams. Check it out, have a look at the link into the description. Now, what actually causes image formation in a lens? It is refraction that causes it. If I have an object across here that is emitting some light as it's passing through, as soon as it reaches the lens, the light will actually change its direction, and it will start moving now this way. So after the light leaves the lens, all of the light will reach what is known as the focal point, because all the rays, as you can see, are being directed towards the same point, and this is known as the principal focus point. Now, straight after that, you're going to see that the rays will carry on, and what we'll do is we're going to get an image of our object, and this is an example of a real image. Anytime we have a real image, you can kind of think of it that it comes after the lens. Also important to know that the image produced by this convex lens, as you can see, is upside down. Well, why is that? Because this top ray is going to go through the focal point and it's going to go down here, meaning that the top of this image will actually be at the bottom here, so our image is actually flipped. Now this is in contrast with a concave lens, which will actually produce something known as a virtual image, which is always kind of to the left of the lens or on the same side as the actual object itself. Now what's the ray tracing across here? We have a ray that goes in here, but now this is also known as a divergent lens, so the ray will move away. However, it's the continuation of the actual ray that will go through here, and if you have one that will go through the center, it will just kind of carry on going through the center. And the intersection of those two rays produces a virtual image which is on the same side. Now this image will be captured by a camera. However, if we were to place a screen across here, then nothing really would actually show up. And also really important to note that with this lens, the image is also the right way up. So this one was going up and this one will be going up as well. Now in GCSE papers, you may come across those two symbols as well. So in ray diagrams, a convex lens will be represented by this symbol across here, and a concave lens will be represented by this. And now let's revise some of the key points on visible light. Now, first of all, each color has its own part of the visible spectrum in terms of the actual wavelengths. So for instance, red will be somewhere within 620 to 750 nanometers. On the other hand, if we had something like, I don't know, yellow, I think that one was around 570 nanometers, etc. Now, reflection from a smooth surface in a single direction is called a specular reflection. So if you have something like a mirror and the light just does that, this is an example of specular reflection. Now, reflection from a rough surface tends to cause scattering, and this is called diffuse reflection. So those are the two terms. Whoops, I've started moving the whole thing. Those are the two terms that we need to remember for the exam. The way color filters actually work is by absorbing certain wavelengths and colors and transmitting others. So you can have, I don't know, like green colored glasses, etc. Now, the color of an opaque object is determined by which wavelengths are strongly reflected. So if my shirt is blue, for instance, this means that it reflects the vast majority of those wavelengths, and the rest are actually absorbed. If all the wavelengths are reflected equally, then the object tends to appear white. If all the wavelengths are absorbed, then the object tends to appear black. And objects that transmit light are either transparent or translucent. Finally, we need to mention what is known as black body radiation, and all bodies or objects, no matter what their temperature, essentially emit and absorb infrared radiation. The hotter the body, the more infrared radiation it radiates in a given time. And what does that mean? This is how night vision, for instance, works, because everything emits infrared radiation. Now, the black body is an object that absorbs all of the radiation that is incident on it. And a black body does not reflect or transmit any radiation. And however, a good absorber is also a good emitter. A perfect black body would be the best possible emitter. In fact, you can approximate something like a star very well with it. So it's just another concept in physics. Also remember that all bodies emit radiation, and the intensity of wavelength and the distribution of the emission depends on the temperature. So for instance, if you have something like a piece of metal, for instance, initially it starts to emit sort of probably something around something that looks kind of like red if we were to start to heat it up. And then the more we heat it up, the more the radiation becomes lighter and lighter, and eventually it starts emitting across all the wavelengths, sort of appearing white. Okay, well, a body at a constant temperature is absorbing radiation at the same rate as it is emitting radiation. And the temperature of the body increases when the body absorbs radiation faster than it, well, emits radiation. This is actually deeply connected with the climate on Earth, for instance, because a lot of the energy is trapped by greenhouse gases, and in general the temperature of the Earth depends on those factors, including the rate of absorption and emission of radiation into space. Okay guys, well, we've done it. We've revised the whole of the waves GCSE physics topic. Well done. And if you're carrying on revising, you need to have a look at this video right over here.